Jump. So what's going? Why is there this black thing on my computer? I guess that's the recording device or something. Sorry about that. Is it up again? Okay. Where's my tech? Sorry about this. Okay, go. Okay, thank you all for. I want to thank the organizers for this wonderful opportunity to come and speak here. I was one of those people here 20 years ago, and I also want to thank my funding agency, NIAID, for the help. But so I was assigned a title called Design and Analysis of Vaccine Trials, but I changed it to Studies, and there's a difference in my mind. And I'm going to talk about some of the things, my own personal view of a few things going on in the last 20 years. So, dependent versus independent happenings. Most of the people in this room know Sir Ronald Ross because of his, he won the second Nobel Prize in Medicine, and also he was a great malaria modeler, and one of the little factoids that I will say is my dissertation was on modeling malaria, and so I became quite acquainted with Ross. I think those models might have been some of the earliest ones, if not the first ones, to differentiate infection, disease, and infectiousness. But there's another aspect of Ross that's maybe a little less known, and that he was quite interested. He developed what is called the theory of happenings, and it's in this wonderful paper in the Proceeding of the Royal Society, where he differentiates between dependent happenings and independent happenings. And in a very general context, he talks about trade unions, and he talks about all sorts of things. But we are interested in the dependent happenings, where the number of individuals becoming affected depends on the number of individuals already affected. And he defined this generally not just for infectious diseases. And I'm going to talk today a lot about how to estimate indirect and overall effects of vaccination programs, because demonstrating indirect effects can have important consequences for global vaccination policies. Now, here's a picture of Hib incidence in England and Wales. I took the data off the formerly known as HPA website. And what you can see is the rapid drop in Hib reports. And worldwide, when the Haemophilus influenza B vaccine was introduced in the late 80s and early 90s, the transmission of Hib just disappeared. And it really made believers of a lot of clinicians that there were indirect effects, because it hit more than just the target population. So going back a little bit in history, study designs for dependent happenings. This is work I did with Claudius Struckner while we were at Harvard in the 80s. And at that time, thinking about different kinds of effects of vaccination was quite chaotic. And one can think of indirect effects as something that's very general, but what we have here is point. Okay, suppose, so we informally defined indirect, total, and overall effects of vaccination. So imagine that you have two populations, population A, population B, that are similar transmission dynamically, and we want to, in population A, you vaccinate some of the people. So in that population, you might estimate what we call the direct effects of vaccine. You compare the vaccinated to the unvaccinated people. And in population B, we didn't vaccinate anyone, and so we might be interested in comparing the effect of the vaccination program on the people who didn't get vaccinated with the people who didn't get vaccinated here, and would call that the indirect effects of vaccination. If we compare the people who got vaccinated, their outcomes, with the people who did get vaccinated over here, then these people would have the benefit both of the vaccination strategy and the vaccine, hopefully a benefit, what could be a detriment, but you would compare these vaccinated people here with the unvaccinated people here, and that's the direct and indirect effects, which we call the total effect. And as a public health official, you might really be interested in what the overall effects of vaccination are. That would be sort of the average here in the population where you had a vaccination program compared to the unvaccinated program. So that's sort of a heuristic definition of this. I'll go into this in more detail. So luckily, I don't get to talk to an audience like this very often, but I'm sure that everybody in this room has the power, either theoretically or using deterministic or stochastic simulations, to assess indirect, total, and overall effects in in some sort of theoretical way. But my interest has always been, since those days back at Harvard, to look at these things empirically. And how would you estimate these things in the field? Okay, so at this point, I'll say I'm going to talk a little bit about the potential outcome approach to causal inference. And I was bit by 2 bugs back at Harvard in the 80s, and one was the dynamic modeling, and particularly malaria modeling of vaccines, and also causal inference, which was sort of more of an infancy in those days. So I'm going to talk briefly about this aspect. It's sort of like my evil twin Skippy has appeared at this conference. So the potential outcomes of an individual, we can think of the potential outcomes in an individual as something that happens. So a person has an outcome with a treatment and without a treatment, or with a control. There's 2 different kinds of outcomes. And people from Penn State don't have to worry. I'm going to give the entire talk that I gave at Penn State, because there's no notation in this. So those outcomes are deterministically fixed, because but the fact is that we define the causal effect of the treatment in that individual as the difference in the potential outcomes if the person had received treatment as compared to the person hadn't received treatment. Now the problem is this is generally not observable, because you can't, in most cases, except for crossover designs, you don't see the outcome in a person with and without the treatment. And the other thing in causal inference, and generally one has assumed that the individual's potential outcomes are independent of others' treatments. And so it's easy to say in the infectious disease world to see that doesn't hold. And that's so since the 1980s, this has been an area of interest to me. So what you do in causal inference is use population averages under some sort of treatment assignment mechanism to estimate average causal effects. And so interference and dependent happenings. So interference is the idea that the potential outcomes in individuals are affected by the treatment status of other individuals. And there's a book by Cox from 1958, not using potential outcomes, but talking about interference. And the problem is, in the presence of interference, the treatment of an individual can result in indirect effects on others. And it's a much more complicated situation in causal inference if you have interference. And College and I, way back starting in the 80s, and we published a paper in 1995, we tried to define causal estimands and estimators for population level, indirect, total, and overall effects. And I can say we failed miserably, and we wrote a paper about the problem, but we never really solved the problem in those days. So just briefly, again, in causal inference, you usually have to make an assumption about the mechanism by which individuals are selected or assigned treatment. And this gets back to something that Chris Dye was talking about, and he showed that hierarchy of believing in information. There's a randomization, and there's different levels, and there was observational studies. And so with a colleague of mine, Michael Hutchinson, in a paper in JASA, we defined the causal estimands and unbiased estimators for individual, group, and population level direct, indirect, total, and overall effects, which I'm not going to go into the detail of which, but this was based on an idea by Sobel, who's actually a sociologist who also published in JASA, but we had the paper back in about 2004, where you're able to average overall possible randomizations, and that's the key idea of the causal inference with interference that we worked with. We averaged over all possible randomizations to get these different estimands. And so we suggested this sequential 2-stage randomization procedure where you would randomize the groups of the clusters that you're looking at to receive a particular vaccination strategy, and at stage 2 you would randomize individuals within the groups conditional on the group allocation strategy. So I just want to now there's an assumption in here that we made, which I won't go into detail, but it's called partial interference, and that's where you assume that these groups receiving the vaccination program are independent of one another, and that you only can have interference within the different groups. So here's just an example, so of a little more formally, of that kind of idea for those of you. So here we again have population A and population B, where now we can see in population B we might have no vaccine, and but we could also have a control vaccine. And that might be one way of thinking about this, and I'll give examples of this that have occurred. So here we might say we vaccinated 70% of a population of 1,000 people, and we randomized the vaccine then to 70% of the people. So we had 700 vaccinated, 300 unvaccinated. And here we have 70 cases, and here 90 cases. So our total attack rate then has 160 cases over 1,000. Now here we could even imagine we have a no vaccine. Let's say I'm going to give an example of a trial that was using a pneumococcal vaccine as the real vaccine of interest, and they used a meningococcal vaccine as a control. So these 700 unvaccinated in that case might have gotten the meningococcal vaccine, so it doesn't have an effect on pneumococcal cases. And so here we have 1,000 people, and the attack rate, of course, in this case of pneumococcal would be the same in the unvaccinated and the vaccinated, and the whole population has 850 cases for an attack rate of 0.85. So in this case, we can look at the direct effect between these people that got vaccinated and didn't get vaccinated. We could look at the indirect effect here between these people and either the entire population, or if we were a little more rigorous, we might want to take these people who didn't get vaccinated and these people who didn't get the meningococcal vaccine, and then total effect again would be between this group of people, the vaccinated and the unvaccinated, or in this case we might be rigorous and have these unvaccinated people, the meningococcal people would be the total, and here the overall effect again would be the average reduction. And in a group randomized trial, you would usually have many more than one group in each of the vaccine arms. And so then we could estimate, sort of using these values, we had the attack rate in the population B of 85, the attack rate in A of 16, and then the attack rate in the vaccinated in group A was 10%, and the attack rate in the unvaccinated was 30%. And these give us our estimates then, just as a demonstration. The direct effect estimate would be 66. The total effect would be 88%. Indirect effect would be 0.65, and the overall would be 0.81. And what we can see here, there's a lot we could talk about, but this is an overall a general talk, that the total effect is higher than the direct effect. And if you didn't have any indirect effects at all, the total effect would equal the direct effect. And so if you just use the direct effect estimate, say to estimate your total number of cases prevented, you would underestimate your effect if you had had this comparison population where you had 80% reduction. Okay, so going on, usually there is no two-stage, to my knowledge, there has never been a two-stage randomization trial in the vaccine world. Usually randomization will occur at the group level. I'll present you a couple examples of that at the individual level or neither. And there have been methods proposed using propensity scores to deal with this, generalizations of the propensity score, which take into account, well, basically the idea of the propensity score is you estimate the probability of receiving a treatment based on observed covariates, and this approach that has been developed now recently is a generalization of that to group level propensity scores. So I wanted to present a couple examples of, this is supposed to be sort of a historical talk, looking at what's going on, and doing these trials is becoming actually of some interest in the last years. There's a really nice trial here that was developed by Larry Moulton and company. They designed a group randomized double mask phase 3 trial of a 7-valent pneumococcal conjugate vaccine that was implemented in the American Indian population in the US. And they had an active control. Oops. It was a meningococcal vaccine. And the goal was to evaluate the total effects of vaccination as well as the indirect effects. And it was at the same time to serve as a pivotal vaccine trial for reasons I won't go into now. And the goal was to vaccinate as many children under 2 years of age as possible. It's a beautiful paper. It's a beautiful trial. Unfortunately, or fortunately, the vaccine actually was licensed before they could, licensed before they could complete the trial, and so they had to vaccinate the people. So they only have a very short period of follow-up in that trial. There's a couple other trials I just mentioned briefly of typhoid vaccine studies. These are, again, group randomized studies. They're not randomized at the individual level like we were suggesting in our paper, but they do have a control vaccine. So this one was in Karachi, and they vaccinated children 2 to 16-year-old, and the control vaccine was hepatitis A, and they actually got the goal was to estimate total effects and they actually got a statistically significant total effect in the children aged 5 to 16 years. A similar study, group randomized again with the same vaccines, same people essentially, doing the two studies. And their goal was total effects with the secondary indirect effects and overall effects, and they did estimate a total effect of 61%, indirect effect of 44%, and overall of 57%. So these are some things that have been going on. There's more going on around the world. There's one that Ira and I are involved with. It's an influenza vaccine community randomized study in Niakar, Senegal between 2009 and 2012, and the analysis is ongoing. And the target population was 6 months to 10 years of age, and the goal was to estimate total effects against lab-confirmed influenza, and our control vaccine was inactivated polio vaccine. There's another one in India that I don't mention here, and there's one that I've heard of, community randomized rotavirus vaccine study that's ongoing. So there's an increasing interest in doing these kinds of studies to estimate indirect and total effects, or total effects. And looking to the future, briefly, some transmission-blocking malaria vaccine. So there is some discussion right now. This is also discussed here about the malaria eradication that has been brought up by Bill Gates. And the transmission-blocking vaccine for malaria is back on the table. And there's an effort that's being funded by Gates to design, to figure out a way that one would take a transmission-blocking malaria vaccine that doesn't have any direct effect on the individual that gets vaccinated. How would we take something like that to something like the FDA to get it licensed? And I also then thinking about this, I thought, well, 20 years ago, almost 20 years ago, I was on the transmission blocking vaccine task force. Where they were looking at a candidate at NIAID at the time, was David Kaslow, and phase 1 was interrupted because of safety considerations. And so this is almost 20 years later, so there's been a long history of trying to develop this. I will also mention, looking towards the future, that we're trying to think of a way to introduce a dengue vaccine in a phase 4 evaluation using a possible stepped wedge design. A stepped wedge design is briefly a phased implementation where the time of introduction of the vaccine intervention to each cluster is randomized. And so we're thinking about that. And there was a really famous study done that was a group randomized design, the original one, hepatitis B in the Gambia, but that wasn't for estimating indirect effects. But it's certainly a nice study to read if you're interested in this area. Okay, so going on then, those are some cluster randomized designs. There's also people making an effort to use individually randomized studies to assess indirect and total effects. So this is randomized at a different level, and you can look at geographic variability of vaccination coverage. And so a famous one is the cholera vaccine trial in Bangladesh, which has been analyzed to death, but it took place in the 80s, and there they had 2 oral cholera vaccines, and it was a randomly assigned, individually randomly assigned to children and women over 15 years of age. And so they had 2 different vaccines, and the placebo was an E. coli vaccine. And it has been analyzed quite a lot, looking at whether there was depending on the coverage, whether you had a reduced transmission. And they did estimate, first of all, the efficacy was lower in areas of higher vaccine coverage, and the risk of disease among placebo recipients was inversely associated with level of vaccine coverage. But this was not a principled analysis in the way of causal inference. There's another one that you might find interesting that looks at the networks in their kinship network and sees that the cholera risk is associated with the level of coverage. Now, there's a paper that I'm associated with that's under revision that uses this methods of causal inference that I've been talking about of treatment, the inverse probability weighted estimators that I mentioned before, using the propensity scores in the presence of interference. And I'm not going to go into the details of that because it's fairly technical for the uninitiated, but if anybody's interested. So we looked at this study, again, the same study that I just talked about, that individually randomized study, and we defined neighborhoods because the neighborhoods are not defined. That's something that's the observational part of this. We clustered the baris, which is where the people live, into neighborhoods, and we pre-specified. The thing we had to decide, we had said there were 700 of them, and we clustered them into neighborhoods, And we did a sensitivity analysis that I'm not going to present. But sort of, you can see here the neighborhood. So this is the area of the vaccination, and this is just a cutout. So here, this would be if there were 700 clusters. This would be if we did a sensitivity analysis on 400 clusters. So the clusters are bigger, and here we have if we have 700 clusters. And I'm going to present the results of the results. Now, this is where the psychedelic sort of glasses come on. This is sort of the meat of the talk at this point. So what we have here, we estimated for this study the direct effects, indirect effects, total, and overall effects. And this gives you an idea of how complicated this can get, because here we have different neighborhoods. Of these 700 neighborhoods, they can all have different levels of coverage. And so we can compare all sorts of different levels of coverage with other levels of coverage and look at the vaccinated and the unvaccinated in these areas of different levels of coverage. So if I just start here with the level of the direct effect estimates, and these are based on a different score, and this scale here is based on the number of cases per 1,000 years of risk. So for example, here we have a direct effect estimate of about 4. On this level is the level of coverage. So for example, this is 30% coverage, this is 60% coverage. And so what we have here is that the direct effect estimate, if you had a 30% level of coverage, the estimate of the direct effect would be you would prevent about 4 cases per 1,000 years at risk. And here, as the coverage goes up, you see the estimate goes down. Here at 60%, we have about a 0.5% reduction in the number of cases per person year at risk. I think we might have to close the door. Thank you. So here's the indirect effects, and this is a pretty wild-looking graph at first view. But what we have here is the alpha level and the alpha. So here would be, again, an indirect effects are comparing people who aren't vaccinated at a certain level of coverage with people who aren't vaccinated at another level of coverage. And so here we have 30% to 60% coverage, 30% to 60% coverage. And what you can see, of course, the indirect effects on this 45-degree angle would be 0, because at the same level of coverage, there would be no indirect effects. On the 0 axis, on this axis, of course, it's 0, because if you have the same level of coverage, the disease incidence would be the same in the unvaccinated at the same level of coverage. And what you can see here, just as a definition to look at the way this is defined, we have here, we'd have 30% coverage or 33% coverage and 60% coverage. And so if you had vaccinated 60% of your people compared to 33% of the people, you would save 4 cases per 1,000 person years at risk. And you can look at this, and it's symmetric around the 45-degree angle, but that's the interpretation. So you can look at this entire graph as a public health person to see what you would say based on the analysis of this study. You could say at which level of coverage, comparing how much would you gain for the indirect effects. And we don't have time to go through all of these other ones, but this would be the total effects, and this is the overall effects. And we can do a similar analysis, but we don't have, it's a very complicated graph, but I just wanted to present you those analyses that we can look then, analyzing these data using these propensity score approach to make an individual randomized study and analyze it in a future principled way. So there's future directions for this, relaxing the partial inference assumption and making, this is where there's a role for network theory. And this is a very hot topic in causal inference. That is, I didn't do it, but in Google Scholar, if you looked at causal inference under interference, it's an exponentially increasing area. So for your reward for looking at that graph is that you get to see the picture of the camel, my favorite picture in the vaccine world. This is to show how important it is to vaccinate children. They have a solar-powered refrigerator to take get the cold chain and to take the vaccines into the back parts of the desert. So just going forward, there's a lot of other things we can do, but I will just wanted to step to the future. The last 2 slides would be another area, two important other areas that are being developed that are really the future, and one is the host pathogen genetics and vaccine and immune response. And we've already discussed the increase in pathogen deep sequencing, and this is being used also. We're also interested in the regulation of the host immune response by individual genetics and the HLA type, the evolutionary pressure of vaccine versus natural infection-induced immune response. There's a lot of work now in the difference in genetic sequences of escape pathogens in vaccinated versus unvaccinated individuals. This was called by Peter Gilbert the sieve analysis. There's been a huge literature on this. Also more computational biology and confirmation of epitopes, antibodies and HLA types. And Trevor will talk about, I hope, the antigenic cartography. And the other area that I don't have time to talk about, but I just have one slide to talk about it, that's a really growing area, is the correlates of risk and surrogates of protection, which is then, it's motivated to replace the phase 3 trials, which are incredibly expensive and under many conditions impossible. And there's a lot of work in the area of causal inference looking at this, which of course would be another talk. So just to finish up back to Sir Ronald Ross, there's a relationship between the dynamic transmission models and the kinds of things we think about in here, and also the statistical methods and causal inference methods for evaluating vaccines and vaccination strategies in the field. And there's a lot of work to do in the future in integrating more dynamic models, especially into the causal inference framework for evaluating vaccines. And so with that, I would like to finish. Thank you.
A quick one. Isn't the indirect effect estimate dependent on the population mixing structure or your assumptions about how it mixes?
So the question is, and I anticipated this, but I had to take out the slide about that. So the question is about whether the indirect effects are not dependent on the mixing structure. They're dependent on a lot of things: the vaccine coverage, the mixing structure, who gets vaccinated. So one of the problems is, and the challenges, is that there's no real I mean, the indirect effects will vary from population to population, and so that's a real. If you estimate 70% here, it might not be 70% someplace else, and that's true. And so that's an issue. I think, for me, it's more important to demonstrate that there are indirect effects than that it's 70% versus 40%. It's very location specific, so that's a good point. Yes?
Can I just ask a bit more about the indirect effect? Because as I understand it, it's a within generation effect. But if you totaled up the effect of all transmissions prevented in the future across all generations, it would be much bigger.
Correct. It would be infinite.
Yeah.
If it works.
Yeah. Well, I don't quite understand why. I mean, maybe I misunderstand. So the indirect effect. I mean, there's a lot of ways of measuring indirect effects. You could say, I want to see at the end of the year, I implement a vaccine. At the end of the year, I'm going to see how I've reduced the attack rate compared to where I didn't vaccinate. And that doesn't have anything to do with generations.
But I think the question I'm asking is essentially, what's the overall effect on the epidemic of vaccinating a certain individual? What's the consequences across all generations?
Well, I think, so the question is, what's the consequence against all generations? And I don't totally understand the question, but there's a lot of different ways you can measure indirect effects. The other indirect effects I didn't talk about was change in age distribution of infection. There's a lot of indirect effects, of course. In 31 minutes, you can't really talk about everything. But I mean, you have to define your indirect effects are defined given a specific outcome. And so you could say, I'm not quite understanding your question. If at the end of one generation, we have a talk coming up, don't we, Brian?
I think we'll continue this later.
We can continue this later because I'll take one more question. Ira.
Well, I think
Ira never talks to me.
just continue that. You could do in the impact. You know, how many cases do you prevent indirectly per year per 100,000 people projecting many years into the future? Is that what you're talking about?
Yeah, more or less. I'll explain it over coffee.
We could talk. Yeah, I mean, how you define your study and the outcome is a relative. It all depends on how you define your outcome.